Hi, thanks for joining me. Today I've got a really interesting number theory problem I want to share with you. We want to find all prime numbers p and q such that p plus p squared plus p cubed plus p to the 4 is equal to q plus a q squared. If you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to dive straight into a solution. Okay, so to solve this problem, what we're going to do is try and bound q and show that q can basically only take a restricted set of values. And the way we're going to do that is actually by forcing one of the sides of this equation, to be a particular type of number. Because currently, both the left-hand side and the right-hand side can almost be any integer with a few restrictions. What we're going to do is have a better grasp of what this right-hand side is. I'm going to choose or make the right-hand side be a square number. And the way I'm going to do that is by multiplying both sides by 4 and then adding 1 to both sides. So if I do that, I get 4p to the 4 plus 4p cubed plus 4p squared plus 4p plus 1. And that's just going to equal 4q squared plus 4q plus 1. And that, of course, is just 2q plus 1 squared. And this is obviously going to be a square number regardless of what prime number q is. And this is quite nice because now we know that this left-hand side must also be square. So not only is it an integer, it's also a square number, which is going to help us because that means we can restrict our search to just looking at square numbers here. Okay, cool. So we need to think about what square numbers are around this size. Well, this is 4p to the 4 plus something, so it's definitely got to be at least 2p squared, then that the guy squared. What I'm going to do is I'm going to add p to this. So if I do 2p squared plus p, and I square that, what do I get? I get 4p to the 4 plus 4p cubed plus p squared. And it's pretty clear to see that this guy here is much smaller than this guy here. So this is going to be less than 2q plus 1 squared. Cool. So we know therefore that 2q plus 1 must be bigger than 2p squared plus p. Okay, let's look at the next square number. So 2p squared plus p plus 1 squared. Now this guy here is going to be, well, the same as above, 4p to the 4 plus 4p cubed plus p squared plus 2 lots of 2p squared plus p, so that's going to be 4p squared plus 2p, and then add 1 at the end. And this is just going to simplify to 4p to the 4 plus 4p cubed plus 5p squared plus 2p plus 1. Now, I encourage you to have a think about why this thing here must be bigger than or equal to this thing here, but it's something to do with the fact that p is prime, and so therefore p is at least 2. But this guy here is always going to be at least this guy here, and in fact, equality is going to hold if and only if p equals 2. So this guy here is going to be bigger than or equal to 2q plus 1 squared, with equality if and only if p equals 2. Cool. So what have we got here? We've got that 2p squared plus p squared is less than 2q plus 1 squared, which is less than or equal to 2p squared plus p plus 1 squared. So these are all square numbers. So in fact, I can just get rid of the squares here. And now I get that 2p squared plus p, which is an integer, is strictly less than 2q plus 1, which is less than or equal to 2p squared plus p plus 1. But these guys here are consecutive integers, and this guy here is supposed to be an integer. And the only way you can have an integer but bigger than this integer but smaller than or equal to this integer is if these two guys equal each other. So we have that 2q plus 1 equals 2p squared plus p plus 1. And now we can use this condition here, that the equality only occurs when p is 2. So we know that in order for this equation to be true, we need p to be equal to 2, and just substituting that into here, say, you get 2 times 2 squared, which is 8, plus 2, which is 10, plus 1, which is 11, so you get 2q plus 1 is 11, and so q equals 5. So the only solution to this is pq equals 2, 5, and both of those are prime numbers, so this works. That is our solution to this problem. A pretty neat idea for solving this problem, where you basically bound a square number between two consecutive square numbers, and that really restricts your search here. I hope this solution has made sense, and I hope you have enjoyed this problem. Thank you for watching. I'll catch you in the next one. Have a great day.